All right. I'm going to talk about why stack memory is awesome. Last year, I introduced myself extensively. I'm not going to do that again, but it came down to I tried a bunch of languages for my studies, and they had their strengths, but I ended up with D because it's a jack of all trades, and I can use it for both high level and low level without the friction of interfacing between languages. In this talk, I'm going to talk about memory. I'll explain the difference between global, stack, and heap memory, what makes stack memory so great, how DIP1000 makes using stack memory memory safe, and some problems and future work of DIP1000. So as a justification for why DIP1000 even exists, memory speed matters because even though my desktop has 32 gigabytes of RAM, only about 192 kilobytes is fast, meaning is L1 cache close to the processor, and the access time of cached memory versus other memory is huge. It's 1 nanosecond versus 100 nanoseconds. And so performance of modern programs is often memory bound. I've had programs where I was fiddling with compiler flags, trying to see is this function getting inlined, and it didn't make a dent, but reducing the size of a lookup table cut the runtime in half. Why memory safety matters? Well, we're deprogrammers, we know that by now. Memory corruption bugs are common in unprotected languages, hard to debug, wreaking havoc. They can cause arbitrary code execution if you're unlucky, and just generally expensive. Now, a bit of a warning about this talk. This might all be moot, because right after this talk, Robert is going to argue why we can make D memory safe by reducing features instead of adding features, as DIP1000 does. So this is either going to be a useful tutorial or a eulogy for DIP1000. So let's start with different types of memory. Global memory is basically everything that you see when you look at the output of an assembler. I have a function here, and on the right-hand side, it shows the assembly. The instructions get put into global memory. String literal I use gets put into global memory. Global variables or variables annotated with static are also put in global memory. Must be all known up front. It is stored uncompressed in the executable. Zero data does not get stored as an array of 0 bytes there. It does just store the length, but otherwise, the array is put in the executable directly. And the operating system loads the executable into RAM when it starts and unloads it when it exits, so it's available throughout the entire runtime. Stack memory is used for function local variables, which are also known up front, but they can't be global because of recursion. A function might end up calling itself again, and then multiple copies of the same local variable need to be stored. So how this works is the OS initializes a region. The size is by default 1 megabyte on Windows and 8 megabytes on Linux, but you can change it with the right linker flags. And this region is used as follows. Here I have a code example of a simple recursive factorial. We're currently in main, which has a stack frame on the stack with all the local variables that exist in that function. And when we call factorial, it stores a pointer to the previous stack frame and pushes the local variables for it on the stack. And when you recursively call the function, it stacks more and more stack frames, which is why it's called stack memory. And then as you return, those stack frames get popped. And then when we go to the next statement in main, write line, it creates a stack frame for that, and the memory we just used for factorial is now used for write line. At the top of a stack, there's a guard page, which prevents the stack from growing past the 1 or 8 megabytes it is and corrupting other memory. This is a page where every time you read from it or write to it, the operating system issues a segfault. The assembly of our factorial function looks like this. At the start, it pushes the frame pointer and subtracts the stack pointer, and that's how stack allocation works. It's just subtracting an integer, adding more stack variables to your function, doesn't add any time. It just subtracts a larger integer. And at the end, before returning, it adds it back and pops the frame pointer again. So it has little overhead. Heap memory, on the other hand, is more complex. It's dynamically allocated at runtime, and the OS provides base functions for expanding and shrinking the heap. And it's often accessed using the C library, which provides malloc and free. In D, we use it through the garbage collector, which is built on top of malloc and free. Operations that invoke the garbage collector and thus allocate on the heap are the new operator, array literals, setting the array length, and concatenating. All pretty simple stuff. So the algorithm to manage the blocks of heap memory is more complex than the stack, because apart from allocating consistently, at any point a programmer might ask to free blocks from the middle of it, and then allocate new blocks and deallocate more blocks. It doesn't just shrink and grow from one end. So there's always research going on to find a better algorithm for efficiently managing a heap. So now we've covered all three. Which type of memory is the best? It's a bit of a trick question, actually. Best is no memory allocation, because often allocation isn't needed in the first place. Like a common example is splitting a string into words and then storing it in an array, only to iterate over the array once, which can also be done lazily with a splitter, which is also provided by Phobos. And then you don't need to stack or heap allocate an array. But when you have to allocate memory, static data works well with global memory. You can use it as long as it fits by using array literals, string literals, or a string import statement which loads a file into global memory. But it's not that great for large or compressed files. When you have a game with large assets, you don't want to load all of them at the same time, because you don't need them all at the same time, and there might not be enough room for all of them. So then you can dynamically read the file at runtime. Now, for dynamic data, what kind of memory is best for that? Please don't use global mutable memory. Global variables make your program hard to test, really complex to reason about, and not easy to multi-thread, which leaves heap and stack memory. So which one is best? Well, you've seen the title of the talk, right? So yeah, stack is way more lightweight and simple. So it's preferable to use stack memory. But sometimes it is, you can't always use stack memory, otherwise heap memory wouldn't exist, of course. So the limitations of pancakes are limited size. We only have our few megabytes region. We can't put too large files on the stack or it will overflow. And also, putting large things on the stack will reduce the cache friendliness of the stack. Here are the default sizes again. You also need to know the size of what you want to allocate upfront, or you need to have an upper bound. And if you put that too high, then you waste a bunch of stack space, which might be bad for cache. You can dynamically allocate on the stack with alloc-a, but that's not recommended for various reasons, which I won't go over right now. And stack memory has a limited lifetime. You cannot return stack memory if I have a static array allocated here and return a slice to it. That slice will point to a stack frame that's popped after the return statement, so it's a dangling pointer. So how can we use stack memory more? Here I have a typical example of creating a string at runtime, just to draw it. So this might be from your game. And we're using format to combine name colon with actual name and pass it to our draw text function. Format returns a GC allocated string, and every time you call it, for every call site, and this alone at 60 FPS creates 172 kilobytes of garbage every minute your game runs, which Might not seem like a lot with 32 gigabytes of RAM in total, but remember, fast memory is at a premium still, and you can multiply this by the amount of times you needlessly make small heap allocations. So how would we do it in C? C is fast, right? So let's take a look. Typically, you would reserve a buffer on the stack as a static array, void initialize it because you won't use most of it, so you don't want to waste time initializing all of it. Then with the sn printf function, we concatenate and build our string, and then we pass it to our drawText function. This is faster, but uglier code. We now need 3 lines for what used to be 1. And is it even memory safe? We pass our buff pointer to this message parameter, and we don't know what drawText does with it. It might store it in a global variable and actually draw it later. And then it would be a dangling pointer as soon as drawNameTag returns. So in C, what you have to do, if you're lucky, check the documentation for pointer lifetimes. Here I have an example of a C function with good documentation, which has a pointer lifetime section saying the specified string is copied before this function returns. In other words, we're good. We can pass stack memory to it. But it would be nice if there was a unified way to signal this property that the compiler even understands, so it can be verified automatically. And this is where dip1000 comes in. Dip1000 is, by the way, not the best, most marketable name. I would call it maybe something more catchy like stack don't crack 64. But for now, I'm just going to keep calling it dip1000. So it adds the scope storage class. Well, it doesn't technically add it. It has been there in the language before, but it starts actually using it and verifying it. So when you annotate a variable scope, it means that it holds something that may not escape the current block that the variable is in. And taking the address of a variable becomes now allowed. And this will infer scope on the variable that takes the address of a local variable. So I've written scope here explicitly, but it's optional. The compiler will infer scope if you take the address of a local and give the same error all the same. So the general rule that dip1000 maintains is for every assignment of variables which have pointers, the VA may not have a longer lifetime than V. So what are these things in quotation marks I refer to? So an assignment is usually just an expression with the equals operator, but there are other forms that are implicitly assigning one variable to another. A return statement assigns it to a variable up the call stack. When you pass it to a function, it assigns it to a parameter, and when you put it in an array literal, it assigns it on the heap. Whether something has pointers, a pointer is obviously a pointer, a slice internally is a pointer and a length, and a class is a pointer to a class instance. Basic types or static arrays and structs with basic types don't have pointers, but if you give them a type with pointers as a base type, then the whole thing will have pointers. And const and immutable shared type constructors don't matter for whether a type has pointers. So variables, the thing about assignments is they're not always directly between variables. It's between two expressions, which may include operators. But what the compiler tries to do is see through all the operators and look at which variables are really there. So slicing a pointer will still result in the same pointer variable. Looking at a struct field will result in just the struct variable being considered. And some expressions may even escape or refer to multiple variables, like the ternary operator. The lifetime is, well, a global variable has longer lifetime than scope variables, obviously. But between scope variables, there's also a lifetime, which is the order they appear in the source code. And this error is important because of destructors. Destructors are run in the reverse order, so when you destruct S1, you don't want S0 to still have a reference to S1, which it could still read in its own destructor and then read a dangling pointer. So in short, dip1000 cares about variables, whether it has pointers and assignments between variables, and not about the exact type expressions or control flow. And this is basically a pseudocode implementation just to show that there's nothing super complicated going on, like complicated algorithms. It's just going over each assignment and checking, comparing lifetimes. So parameters can also be annotated return scope, which is like the in-out of lifetime. It means if I put a scope variable in, I won't escape it by assigning to a global variable, but I may still return it, so the compiler keeps track of it. And if you don't put a scope variable in, then the return value won't be a scope variable either. Return ref applies to ref parameters, which are internally passed by pointer, but from a high-level point of view, they're not actually pointer types. If I add scope to a ref int, it doesn't do anything, because int doesn't have pointers, so it will just be ignored. And ref has, in a way, scope built in, because when I take the address of a ref parameter, I cannot assign it to a global variable, because the ref parameter, there's no restriction to what you pass it to, so it might be a local variable, which may not be escaped to a global variable. So with return ref, you can return the address of the parameter, and it's similar to return scope. But here the rule is when you have a local variable in, you get a scope value out. So not just scope local variables, all local variables. And here's an example of that. Local isn't scope. It couldn't even be scope because it's just an integer. But when you take the address of it, the resulting pointer will still be scope. So this is an overview of the parameter storage classes. The syntax is often confusing with return ref and return scope, but it basically comes down to what am I doing with the parameter? Am I taking the address, returning the identity, or only reading it? This does get a bit tricky with arrays, though, because static arrays and dynamic arrays have similar operations, but notice how they are in different rows. Because when you index a dynamic array, this will dereference the pointer, and when you slice it, it returns. It's an identity operation, while for a static array, indexing is an identity operation, and slicing it will take the address of a static array. So how do return scope and return ref apply to member functions? Member function access implicitly accesses the variable through a hidden parameter called this, which is not specified in the parameter list, but if we turn it into a free function, it would look like this, and the struct instance is passed by ref. Now, if we would like to add const to the this parameter, for a member function, we would put the const behind the parameter list. And the same applies to return ref. If you want return ref to apply to a member function, then it also gets put behind the parameter list, which does look a bit silly, having a return keyword right there. And in fact, last year in my Lightning talk, I made fun of that by compiling this obfuscated example. But yeah, that's how it works. So we'll stick with it for now. So going back to our example in C, how do we make this more tidy and safe? We can do this by defining a struct and putting the buffer in there, specifying a length and a function to slice the right amount of that buffer, and add alias this to implicitly convert it to it. Then add a function which void initializes such a struct. By the way, you can put void in the struct itself. I mean, you can do it, but it will still zero initialize it currently. And then we concatenate the strings with slice operations and return the structs. And with named return value optimization, it will be put on the caller's stack. And then we can just use it like this, which is a lot nicer. But is it safe? We're still passing a address to stack memory to our draw text function, which we did annotate with scope. But does the compiler know that it has to be scope? If we remove scope from draw text, will it fail to compile? Well, if we look at our toSlice function, we need to tell that when the stack string you call this on is a local variable, the return value, the char array, should be a scope value. So which annotation are we going to use for that? Well, if we look at the compiler's error output, it says it escapes a reference to parameter this, and it says perhaps annotate the function with return. So we use return and not return scope, because return scope doesn't apply here. The stack string doesn't have any pointer members. But this is actually a trick question again. We don't annotate it with return. We use inference. It's way better to let the compiler infer the right return annotation. And in auto-return, nested or template functions, scope, return scope, and return ref are inferred, just like other function attributes. And a further improvement we could add to our stack string is use malloc for larger sizes, which exceed our buffer, and then call free in the destructor. And I don't have time to show that all on one slide, but there's an example of that in Phobos, temp C string, which is used to convert a slice to a C string using stack memory for small strings. And DMD uses internally the small buffer structure. Unfortunately, there is not a generic reusable public stack allocator like this in Phobos, as far as I know, but that would be a nice improvement. So gotchas. DIP1000 is known to be confusing. One of the reasons is the scope transitivity rule. Scope is a variable storage class, not a type constructor, and it only applies to the first indirection of a variable's type. So you cannot take the address of a scope variable, which catches many people by surprise. They try to maybe add another scope in parentheses, but that's not how it works, unfortunately. And also, when you dereference a scope pointer, the result, even if it's still a pointer, will not be scope anymore. And as a result of this, scope doesn't work that great with classes, because for classes, their member functions pass the class instance by pointer, not by ref. So you cannot store a scope value in a class, because scope applies to the class instance, not the members. So you can only use scope to safely stack allocate a class in the Node.js code, but you can't store scope variables in that instance, at least not in safe code. For it to be safe, class constructors and member functions need to be scope, which they are in practice, but they're often not annotated as such. A typical constructor like this still needs to be annotated safe scope, even though it is pretty obvious. So that is a source of friction with using classes and scope. And then there's, of course, our favorite return ref scope ambiguity. A variable can be both ref and return scope, or both return ref and scope. And as you notice, these are the exact same three keywords. So how does the compiler distinguish the two? By the order. The order return scope is always recognized. When you first have return and scope, it's recognized as return scope, and other orders will result in return ref. And this looks particularly weird on member functions where you have no ref in addition to the other keywords. So yeah, scope return means something else than return scope, but again, if we make this a template function, it will be inferred, and we don't have to look at that mess. So while DIP1000 is very confusing sometimes, you see that the underlying ideas are pretty simple. And so if you look at the issue list and search for DIP1000 issues, you get 146 issues? What happened here? So a bit of history of the development of DIP1000. In 2015, DIP25 introduced return ref, and it got implemented. And in 2016, DIP1000 was born and accepted. But it's superseded. It's outdated now. The things it says are no longer true, like you cannot attach a scope to a return value. That doesn't work anymore. And it's superseded by the implementation, because as you implement things, you might find new, better ways to do things, and so it started to deviate from the specification. On top of that, DIP1000 is actually a breaking change, which is weird, because taking the address of locals wasn't safe before, and now it is. It should add more code and not reduce the amount of valid code. But there was a big bug in safe. While using a pointer was not allowed in safe code before DIP1000, slicing a static array would just pass, and the compiler would give no lifetime restrictions on it. And much existing code relied on this fact. So in order to reduce breakage and give time to transition, a transition flag was made and renamed DIP1000, and it's now consolidated with the other preview flags. So is the switch ready to use for programmers? Well, it wasn't at the start because there are linking issues. Phobos is pre-compiled without DIP1000, and scope is part of a mangle. And a mangle is an encoding of a function name, including the return types and parameter types, which will be used for linking and overloading. With DIP1000, scope would be inferred, and a little m would be added to the mangle. And without DIP1000, it wouldn't. So linking DIP1000 code with non-DIP1000 code would give issues. But this was solved by making inferred scope not part of the mangle anymore. We're now in the year 2017. In 2018, an extension was added. So unlike the regular return scope that returns to the return value, a special rule was added that if the function returns void, then return scope wouldn't make sense. But you can make it return by assigning to the first ref parameter, and then the lifetime would be transferred to that, which seems like a weirdly specific edge case, but it was because Phobos had a common pattern of assigning parameters to a struct through a constructor or op-assign method. And in this case, you want to be able to assign a scope variable and make the resulting struct scope. And since struct member functions have a hidden first ref parameter for this, that's why the first parameter rule was added. This way, no new syntax was needed. But it was a bit confusing. So yeah, with return scope, this is now allowed to assign stack variables. But at this point, Walter was the only person in the world understanding DIP1000. So this pull request sparked a big discussion because other contributors were begging for documentation. What is going on? Why are we adding this? This wasn't in the original DIP document. But eventually it got sorted out. And as of 2019, Phobos finally compiles with preview equals DIP1000. In DConf Online 2020, Matthias asked, do you have a question?
No, I was just going to comment that it was trivially obvious to the most casual observer that
yeah, the opinions differ on that front. So in DConf Online 2020, Matthias asked, is there a plan to enable DIP1000 by default, and what's the timeline? It's been like 4 years now. And Walter said, oh, we could do it now, and added, well, the spec needs to be finished because documentation was still kind of lacking. And Attila added, we need to turn on warnings for DIP1000 violations because people don't use the switch and they need to be kind of reminded like, hey, update your code. And in 2021, this is where my involvement came in. So one day I was writing safe, pure DIP1000 code, like a good boy. And I got memory corruption, despite safe and DIP1000, because the compiler wrongly stack allocated an array literal. So the compiler has this little shortcut where even if there's no scope annotation on this character array parameter, it says, well, it must be scope because the function is pure. There's simply no global variables or other parameters to escape to. But it didn't take into account the return value. So even when you returned the parameter, it was like, yeah, that's scope. And so when you call it with an array literal, well, the array literal won't escape G, so I can stack allocate this. And then when you return it, you return a dangling stack pointer. So I posted about this on the forums and started fixing it. It turned out a lot of code relied on this bug. And so I went down the rabbit hole and fixed a bunch of Phobos and also uncovered more and more issues about the implementation of DIP1000, which I also posted about. But I got to work on fixing those, and by 2022, I made DIP1000 errors consistent, and deprecation warnings for DIP1000 were now enabled, which was what Attila wanted. So with preview equals DIP1000, scope violations would result in an error or the function inferring system. In system code, lifetime checking is permitted. And in default, without any compiler switch, it would warn in safe code and in inferred functions. It wouldn't infer system, but when you call that function from a safe function which has a DIP1000 violation in it, it would warn about it then. So basically it would print every error you would get if you were to actually switch to DIP1000 but as deprecation warnings. And as of a few months ago, they're now disabled again, because it turns out the transition is still not very smooth. Some projects have a litany of warnings that are hard to fix, and there's still some work to do to make the transition a bit better. So what were some of these past issues that I ended up fixing? The initial implementation for checking if one scope variable was declared earlier than another scope variable was with a global variable incremented in the constructor of variable declarations. The assumption here being that the compiler would, in any case, create variable declarations in the order that they appear in the source file. So is that the case? No. Parameters are created later than local variables, even when they are earlier in the source file. So an extra check was added for parameters, and before you know it, it grew into this mess, which also took into account temporary variables for each variables. And it had a fallback, which looked at the line number and column number of the variable. So I managed to fix this and reduce it back to just one simple comparison by incrementing the sequence number later, not in the constructor, but just before semantic analysis of the variable, which is not like the greatest, but it's a lot better than what it was before. Another common issue is code duplication. Here you see the code from both the caller and callee perspective, which checks if extended return scope semantics apply. So whether you can return by assigning to the first variable. And it's supposed to be the same. If one of these deviates from the other, then the compiler allows memory corrupting code, which is bad. So I refactored this into one consistent function. So both the caller and callee use the same logic. And not just between caller and callee there is code duplication. The compiler internally doesn't put this parameter in the array with the other parameters, so it always has to be checked separately, which causes duplication. Escape by value and reference are very similar, but completely duplicated. The different ways of assignment are also duplicated. What often would happen is there would be an overfitted bug fix, where someone files a Bugzilla issue, and then Walter would open a pull request which fixes only the issue's code snippet. And I would ask, what about the other cases? You fixed it for normal parameters, but it's still broken for this parameter. And then the response would be, that's a separate issue. So open a new Bugzilla issue. And so that's often what happened. For example, with the return ref scope ambiguity, even the compiler was confused at some point about the whole ref return scope thing. So there were tons of bugs with that. And Walter would repeatedly say, it's fixed now. And I would say, no, it's not. It's fixed here, but in these other copies of the code, it's still doing the old thing. And there would be pull request after pull request after pull request trying to like, oh, is it fixed now? Is it fixed now? Until eventually it basically is. And this culminated also in this nice post by Timon. Timon has emailed his frustrations about DIP1000 and also mentioned in his talk how with tuples the scope lifetimes would be conflated. And Walter would often defend DIP1000's soundness by saying, well, all Bugzilla issues I saw were fixable. But Adam succinctly put it as, well, yeah, you can put it in Bugzilla, but the fix will probably be if code equals that, error, nice try, Timon, which would close the issue, but doesn't, it's like plugging holes in an infinite cheese grater, I think was the analogy that was being used. So some of the issues that still persist to this day are the scope inference, which isn't very great. So how it works is basically, at the start of function analysis, parameters are flagged. They may be scope, and every time you do something, like take the address of it or assign it to a non-scope variable, the flag would be taken away. It's not maybe scope. when you return the variable or a reference to the variable, it would offer return ref or return scope. And at the end of function analysis, all the variables that survived and still got their maybe scope flag are turned into scope. So this is killed very easily by assignment to temporaries. If I have a parameter p, which may be scope, and I assign it to a variable which is not explicitly marked scope, the compiler gives up and says, yeah, p may not be scope anymore, even though p2 isn't ever escaped. Also, when you assign a scope parameter to another parameter and then return that parameter, it will infer return on R, but not on P, which is where it's got its pointer from. So there's missing return scope inference on P, which is also not sound. I started a pull request to improve this, which would, when you assign two variables, kind of create a link between P and R that says, oh, if you return one, the other must be returned as well. But the code is quite complex, and it's blocked currently, so there's still work to do to make that work with all the existing complexity. This is the issue that Timon talked about, reduced a bit, where nested functions, they return scope variables from outside their own scope. Internally, this happens by going through the hidden this parameter, which encloses the enclosing function. But dip1000, unlike with structs, where early on it rewrites outer access to this.s, with nested functions, it's a bit more complicated, so still work to do there. I've also started working on that, which also has its own issues. Mangled names. So remember how inferred scope was ignored in mangles? Well, guess how the compiler internally compares types for equality? By their mangle. So this causes some internal inconsistencies where it thinks two functions where one has inferred scope and one has no scope are exactly the same when they aren't. So the solution is to have the same scope inference with or without dip1000 and then include inferred scope in the mangle, which is also work in progress and breaks other code. So apart from issues with the implementation, there are also some limitations in its design. So we've already seen that scope is not precise. It applies to a single pointer object and not individual struct members, so the lifetimes get conflated. There's only one level of indirection. Also, it doesn't support resizing memory. So Attila made an attempt with AutoMem to create a vector type which you can dynamically expand and shrink without the garbage collector, and you can use the slice operator to borrow a view of it. But then when you call reserve or resize the vector, then this should invalidate the borrowed slice, but it doesn't, so that would result in a dangling pointer. Now, the successor to dip1000, dip1021 and live, attempt to add an ownership and borrowing system, but they're not sound. Manually freeing or resizing memory is still system, and they don't enable any new safe or trusted code, so it's basically a bad deal right now. So some final notes. General lessons I got from fixing those bugs were, well, some obvious ones: tests and documentation good, code duplication bad. Also, it's important to find the root cause of the Bugzilla issue and not just fight the symptoms, or else the Bugzilla issue will just come back, and your code will only get more complex while not moving to a better code base. So it's important to fix the unstable foundation. I really liked the bug fixes where the diff was completely red. I could remove all the kludge because the base was fixed, instead of the bug fixes which added more if statements for the Bugzilla issues. And reject valid bugs are better than accept invalid bugs. So a common theme was that dip1000 would be too lenient, and then the existing code would rely on the bugs, and then when you fix it, it breaks code and it slows down the improvements. So my final verdict about dip1000. In general, for memory, if you want high performance code, prefer no allocation or stack allocation over heap memory. diff1000 is a nice, simple idea, but unfortunately it has some complex execution by the way it's implemented, and also the syntax with the keywords is a bit unfortunate with the scope return and return scope confusion. And it works best with flat data, because scope is not transitive, which personally I haven't found to be that bad, because when I write high-performance code, often it's useful to convert your data structures into flat data anyway, because even when you're not accommodating for the limitations of scope, it's a useful thing to do to make your memory more cache-friendly or GPU-friendly. And that closes my presentation.
All right, so it's a question time. Attila's got one down the front. And again, I am looking at Discord and YouTube.
Two statements and one question. First of all, I think that's the first time I understood return scope ever, so thank you for that, and also well done. Two, you said that there wasn't any allocator in Phobos that did the stack thing. There is. You can use a fallback allocator with in situ and then whatever you want afterwards, mallocator GC. And the question is, if you could go back to that sequence number bug that you fixed.
Yeah? Which one?
Yeah, so that. Won't this break with separate compilation? Because the number won't be incremented the same way?
No, because the sequence number is only used within a function. So it's not that there's two functions and the sequence number in one function are compared with the other. It's only when you analyze a function that the sequence numbers are used, and you cannot separately compile the first half of a function and the second half. So.
All right, good, thanks.
I also want to compliment you, Dennis, on doing a very difficult job with this. I appreciate it. Not many people have been able to do the kind of work you do with this. So thank you.
Thanks.
So one thing I think we could use in the maybe scope flag or whatever that is something to say, definitely don't want this variable to be scope. Because a lot of times you declare it and you say, how did this thing become scope? Because I wasn't intending it, but it just happened to be where it got assigned first or whatever.
Like for a parameter or a local variable?
Local variable. To be able to say, this local variable, I want to make sure it's not scope.
Yeah, there is a trick you can do where you take the address of it, cast the pointer to an integer, and then cast it back, and then it loses the whole scope thing, but it's kind of a hack.
Nice to see something else.
Yeah.
Any more questions? No? Really? Even the amount of conversation around DIP1000.
I explained it so well, all the confusion is now out of the world.
You've really got nothing to say now. Jeez. All right, let's call it then. Give it up. Oh, wait, one more. Slow down.
Sorry, guys. So to continue on what Steven said, in DIP1000, you have this weird behavior where you can declare a variable, let's say a pointer to int, and then later on you do something and it turns it into a scope. What's your take on that?
Like what Steven said, that sometimes scope is inferred when you don't want it?
Yeah, other attribute like static or immutable, you declare it at the variable declaration point, but in DIP1000 it can just gain scope a few hundred lines down.
I mean, like I would prefer to not add anything, and just unless there's really compelling use cases, I would have to see some specific examples and see if really there's not just a nice workaround. Because personally, I haven't found the need very often to cast away scope. Usually I just use a trusted function annotated with return scope or scope. If like the checking has a bug, then I just add trusted to a small piece of code which should be allowed, and then that works.
The easiest way to make it inferred as not scope is assign it to a static variable.
Yeah, but
It's super easy, and you don't have to ever read the value from the static variable. You just assign it, and the kernel will go, oh, I can't make this scope.
Yeah, that's a bit ugly because then it generates a pointless static variable. It just,
Right, but
I mean, it's only 4 bytes or 8 bytes, but still, it's kind of ugly.
yeah, but it doesn't involve any new features or anything.
Yeah, okay.
You know, new features mean more bugs, so you know.
I suspect you could create a global static array of 0 size and assign to its first member inside an if false, and then you won't have any litter.
What?
You can do that, but the issue here with what Matthias is saying is basically that it does the beginning bit of some data flow analysis and then stops. So it will, the fact that it changes is you can get used to that, but it's more that if you do something that means if you had a full data flow analysis pass, it would be considered not scope again. It doesn't actually, if you think about it inductively while programming, it doesn't actually do what you might expect it to.
Yeah, so you're relying on the limitations of the inference, which is not a great idea, right?
Yes.
Yeah. Because they might be improved later and then it breaks. You know.
So it's just one more rule.
All right, I think that's that then. All right, now you can give it up.